Hello everyone, welcome back to the channel. Today we are diving with the topic that is how you can implement the SVM using Iris dataset with the real-time example. In my previous video, I have already explained about the basic intuition behind the SVM, why you should use it and why you should use it over the logistic regression, number 2. And number 3, what is the support vector? Number 4, what is the margin? What is a linear separable, non-linear separable, and what are the kernel tricks. I did not explain the kernel tricks in detail, but I will show you today practically these are all kernel tricks too. Okay, so now here this is your iris dataset we are going to use classify the type of the flower. As might be you are aware with the iris dataset because this is very popular dataset and this is the best dataset for classification actually. And this video is perfect for everyone, either you are a beginner, intermediate or professional. So here we have a sepal length, sepal width, petal length, petal width, and this is the target. Okay. So I'm just assuming that writing the dummy values. This is not from real data set. Okay. And based on these features, we need to classify whether it is a flower type 1, 2 or 3. Okay. So now you can see there are three outputs, right? There are three classes. So this is called multi-class classification. And what we are going to do? We are going to apply SVM today on this. Okay. As I told you in my previous video, SVM work for SVC classifier and SVR. Okay. Now I will explain you today SVC in detail. How the SVC work actually. Okay. Let me drag it upward. Okay. Now look at these two graphs. Whenever we want to show the data like the visually, right? How using the SVM, it's a good. I have considered the only two features here. Okay. You can assume it. I have considered the petal length and petal width. Okay. And this is your flower 1, this is flower 2, and this is flower 3. Okay. So we are just assuming. Okay. So we have denoted it with the class your 0, 1, and 2. So what we can do, we can name it with the same. So there will be the no confusion. Okay. So this is the your class 0. This is your class 1 and this is your class 2. Okay. Now when you are going to apply the SVC like a model from the SVM, okay, so it will separate the what it will do, it will classify or separate the class automatically based on the this method actually, because SVC work based on a two, like the at the behind it work based on the two strategy, OVO and OVR. Okay, so I will explain you first what is OVO. Okay, this one. So in this when you apply the SVC model on your multi-class classification, okay, it will by default use this strategy. This is one class versus other class. Okay, so it is going to separate the each class from the other class, but it will take it as a pair. Okay, like for example, so what is your green? This is the one, this is your class 1 and this is your class 0 and this is your class 2. Okay, so when you apply the SVC, okay, by default you don't need to mention anything. You need to separate the classes, you need to classify the classes based on one versus one. No, but automatically it will pick up this method actually. At the back end it is working like this, your SVC. Okay, and it will draw the plane in between. Okay, it is going to draw the plane. This is the line it is showing now, boundary, right? So first pair it pick up the 1 versus 2. So what is that? Your this class versus this class. So first it will draw this line. This is going to be your line. Here we can write it. We can change the color. This is your first boundary actually. Okay, using the SVM. So what it does, it separate your class 1 from class 2. Okay, like this way. But you can see there is some overlapping too. There are some like the data points which is coming from class 2, it is also coming into class 1 too, right? Same from the class 0, right? So this is a misclassification also lies. So there is a high chances because this is 2D and the data is overlapping, right? The data points is like in this form and we are trying to separate it linearly. Okay, that's why it's overlapping. Now the second case, it pick up the two classes 0 versus 2. So this is 0, this is 2. Now it will draw this line, this one. Okay. So this is your second line. This is a second plane. Okay. It draw the SVM and it separate the your class 0 with the class 2. But you can see here, this is also the overlapping, right? These data points are also belonging to now class 0 and there is also the someone, right? In the third case, it pick up the 0 versus your 1. Okay. Yeah, it's a 1. So 0 versus 1. No, it's a 0 versus 2. This one. 0 versus 2. So in this case, what it is doing? This is your third one. Okay. So it is going to separate with this line. Okay. Now this is 0, this is 2. But still there are some cases where they are overriding. Right? So this is the linear separation. This is the functionality. It will pick up your classes pairwise separation and it will try to separate it linearly, right? Linearly means what? Just to draw this one plane, okay? And there will be a one boundary too, which is not shown here, okay? So we can remove this one, okay? So if you want, we can draw the here boundary too. So when it will do the 1 versus 2. So this is your 1, green one, and this is your blue is 2, right? When it is drawing this line, so there will be some boundary too, like this. It is not shown here, but it is something like this. If you don't know what is boundary, you can watch my first video about the SVM, intuition behind the SVM, okay? So this functionality I wanted to share with you. By default, your sport vector classifier use this functionality for your multi-class classification. But by default, your SVM belongs to binary classifier with only two, like your two classes. If you have the two classes, it's very easy to separate, right? Like this. If we make here something like this, let's say here is a one class, right? And we can pick up another color. Here is another class. This is a binary, right? So it's very easy for the SVM. It will pick up like this and create the plane, the boundary. That's it. But here this is not the case. There are one more class, right? So this is the functionality behind your SVC. If you are going to use, it will use this OVO, pairwise class separation. And if you look at the on this left side, this is called OVR. This is one class versus rest. But this functionality is not by default actually. This is not by default. Okay. This is by default. Even if you don't mention, you apply this SVC, it will definitely, it will backend at the back and it will pick up this one. But if you want to apply, you want to separate the one class from the rest of the class, if you think this will give the more accuracy to your model, then you can try this model too. Okay. Here you need to import the OBR. Okay. I have written the code in my practical notebook for your homework. I will make you understand this functionality and this you can apply yourself. It will help you to understand as well about the iris dataset, how the SVM work as well. So you will learn both ways in this case. So this video is very, very beneficial for you. Okay. Here what it will do? It will do nothing. let's say first time it pick up the class 1. Okay. So when it will pick up the class 1, it will draw this boundary. Okay. So it will separate the green class from the other two classes. Okay. And when it pick up the class your 0, this one, it will draw this boundary. So it will separate the green and blue class from the red one. The class 0 is like separate from class 1, class 2. Same with the blue one. Okay. So this is the case. That's why their boundary line I have colored, I have made the color on this so you can understand the difference, because here we are applying at the back end the strategy to classify for the type of the flower based on the this methodology, one versus rest of the class. Okay. But by default, this will be followed by your SVC. Okay. Now this is a linear separable actually. Now don't think these are the different model. These are these both two are SVC actually. This is not a type of SVM. Okay. This is just the extension of SVC your model. Okay. This is just the extension. So whenever you have the multi-class classification data set with you, then it's better to you can try both OVO and OVR. Okay. And then now I will show you from 2D to 3D, because 2D it's looking very tough, right? It's hard to separate them, right? So you can use a kernel trick here. Okay, and you can here kernel trick, same kernel trick we are using above, we are using here kernel is equals to RBF above 2. Here you are also going to use the same. Okay, RBF. But there are other kernel tricks too. I will show you in the practical example. Here we are increasing the actually number of features. Here you have taken the only 2 features. Here we have increased the feature. We have increased the dimension. Now we convert the 2D dimension into 3D. That's it. Okay. So there are 3 features. Based on that, we are applying the SVC. This is OVO. Sorry. And this is OVR. You can see it seems to be better, right? If we compare here, it is not looking good, right? It's looking overlapping is everywhere. But now if you look at it, it looks little better, right? It's easy to see and understand. So this is just a 3D view. More than that, we can't view, right? It's very tough to visualize more than 3D. It's not possible. So that's why whenever we apply the SVM, our goal is to just, you can reduce the feature, whatever it is required, you can use them. And maximum, you can choose the 3 features for the your classifying the type of the flower, right? Otherwise, it will be very hard to draw the boundaries. Okay, it will misclassify the data more. So this is just, I wanted to let you know what is a OVR, OVO. These all are a extension of your SVC, and by default, it use OVO, one class versus other class. Based on that, it classify or create the plane or the your line to separate them. And in the OVR, it creates the boundary between one class to the rest of the classes. Okay. Tomorrow you might have a more than 3 classes too. Okay. So you need to apply both. By default, it is going to be applied, but you can try this one too. It might help you. Okay. So this is about the just basic definition about the your multi-class classification using SVM. Now we will jump on to the practical example. Okay. So let me share my screen here. Here we go. So I will give you the little homework today. Once you tried this one, you can read those questions, complete the questions, complete the notebook using the same notebook and send back it to me. Okay, send it back to me. I will definitely assess your like the work and also give you the feedback. Okay. Now look at this. So first of all, we will import the libraries. Here I have imported the scikit-learn dataset import load iris dataset. Using this, you can download the iris dataset directly from the scikit-learn dataset library too. But I have imported from the Kaggle. Okay, so I have uploaded the dataset. So this is the same method. we need to load the data set. This is CSV, read underscore CSV. And then this is, we are making the copy of your original data set because we don't want to make any changes in the original data set. And then we are using the head method to show and explore the data set. Okay, so you can see here sepal length, sepal width, petal width, and this is the type of the flower you need to classify. Okay, now you can see this is also the high dimensional data, right? If it is like a small data set, it's easy for classifying, right? But it's very hard now. And then here we are just looking at the information. So we have a 150 entries and it contains the 5 columns. It's a data, it's a target variable is of object type, rest are of the float type. So we need to convert our target feature into the numeric before we build the model. Okay. And then here is the describe method. Here we are just talking about the statistics of the each feature. This is the count, this is the mean, this is the maximum value. It also gives you the idea about the outliers too, if the maximum value is very far away from the mean. Okay, and this is the interquartile range. Okay, and this is the minimum value, this is the standard deviation. If you want to understand it, you can watch my statistics playlist. Okay. And then we are checking the missing value. This is a normal process which we are doing for the EDA. And duplicate, there is a one duplicate, we drop it. Okay. Now we will start with the visualization. Visualization, you know, very important. Okay. Especially when you have a high dimensional data and you want to show the correlation, it's going to be very tough. Okay. So what we will do, we will draw the first pair plot. This is a very popular graph. It gives you the clear vision about the each feature. Okay, if there is any overlapping happening, it will also show you that overlapping. So I'm using from Seaborn, pair plot, EDF, hue, flower name, and then diagram kind is KDE, kernel density. Okay, so we are just diagonally, we always look at it diagonally, the pair plot. Pair plot is useful, very useful here, especially for this data set actually. Okay, I will tell you how. Look at this now. This is sepal length. Diagonally, we are looking at it, right? So this is petal length, petal width, sepal width, now sepal length. If you look at the KDE, petal width, they seems to be less overlapping, right? Look at this, right? So this is your, the blue one is your Sutitsa flower, right? So this is clearly separate from the other two flowers, right? If we look at this graphically and look at this is Virginica, this is versicolor. So there are some, there is some overlapping, but it is very clear this is less overlapping. Same here for based on the feature of your petal length too. They are clearly separated. There is some overlapping, but they are not too much overlap. But if we talk about the sepal width here, look at this, highly overlapping, right? So if, just think here, if you are going to use the sepal width, right? You are going to use the sepal width to classifying the type of the flower. It will be very hard for your model to classifying them, right? To separate them into the different, like the your classes, right? How they will classify this is versicolor, this is setosa, this is virginica, because they are their data points is so overlapped, right? Look at this, it's the same here. It's too much, but it's a little bit better. But these two sepal width, sepal length is not doing well than the petal length, petal width, right? So here you can just start thinking these two features are more beneficial instead of these two, right? During the model building. And then if you look at this petal length, this is also looking at very clear separation. Here there is a no relationship, right? Not too good. I will not say no relationship, but if you look at the here the type of flower setosa, right? If the petal width is increasing, sepal width is increasing, the petal width is increasing, it is not making giving you the type of the flower setosa. So this means this is not connected with each other, right? And if you look at the sepal length here, look at this distribution, right? So this is the way how you need to look for the distribution here. Okay, and this will give you the idea which features are important. Okay, Now we have another graph too to check the correlation. So we are picking up, and now look at this. Petal length is 87% highly correlated with the target. Look at this, 96% petal width. But if you look at the sepal length, right, and sepal width, it is negatively correlated, right? Sepal length is still good, 82%, right? Here, the sepal width is not good. Okay, so this seems to be like less correlated. Okay, and this is called the correlation heat map. And here, the higher the red color, this is a like a positive correlation, and below this is the negative correlation. So it is showing the positive, negative, both correlation. Based on this, you can also select the features. Why I am forcing you, like saying you again and again this thing, you can select the features, because we want to show actually SVM, right? Based on the binary classification, okay? Using the two features. So we can see them, how the SVM is working correctly. So you can choose the two features. You can choose the randomly too, but it doesn't make sense. So I'm just like telling you how you can select the feature. Okay. In my previous videos with the practical example, I have showed you the many method for the feature selection. So we are using this one here. Okay. And then we are just drawing the box plot too. Okay. For the distribution of the data. Now look at this. This is your Setosa, versicolor and virginica. This is sepal length and sepal, oh sorry. Yes, this is a sepal length, right? So Setosa. So it's telling us we have the Setosa value here. There is a one data points which is very far away from the mean, right? Virginica, this one. This has a good amount of the like the sepal length, and we have the data, right? It is able to predict this one, but in case of Setosa, it is not doing like any major thing, right? We have a very small like the records in this. This is the median. This is the maximum value. This is the minimum value. And look at this sepal width, and this is the one, right? This is about the sepal width. If sepal width is this 4.5, the setosa is there. Okay, and if the sepal width is maximum 3.5, then it is a versicolor, right? So this is just the distribution of the data. Now look at the petal length. In the petal length, right? The setosa, you have a many like the data here, right? This is but between the 1 to 2 petal length. Okay, when you have the data records with the 1 to 2 petal length, either it's in the centimeter or what, right? So this is going to give you the setosa flower. This is the records you have. And this is the your versicolor. The petal length should be between 4 to, we can say 5.5. And if it is this length, like from 5 to 7, this is going to be virginia. Same here with the width. Okay, so we are just looking at the distribution of the data, how many records you have based on the petal length, petal width, or what will be in what range you have the values of petal width and what kind of the flower it contains. Okay, and then we have plotted the violin, your violin plot too. This is also very beneficial based only on the petal width. Okay, so this is the petal width. So here your box plot is inside it, but it is showing you the distribution outside it. So that's why we use it actually. Okay. Because here you might be not too much clear, but here you can see wider is the violin plot, good is the data points. It's very simple. Okay. And the white line which you are looking at it, this is the median. Okay. Median value of it. Now this is just a small visualization. I just wanted to show you. You can draw other graphs too if you want. If you don't know what kind of the data or what kind of the graph you should draw, then you can check my playlist data visualization. Okay. And then we will build the model here. So under this, you will also learn the SVM kernel trick too. This is very popular. Okay. So first of all, we will work on the linear SVM on two features. As I told you, I showed you in the start on the whiteboard, whenever we are applying the SVM, its main goal is to create the hyperplane to classify the two classes which I have explained very well in my previous like the video too. I'm telling you again, if you have a two like the features, right? And the two classes, you want to separate them, it will just draw the one line. This is very easy. But if you have a more than that, then you need to convert them into 2D to 3D, which I will show you after this example. But first, we will pick up just with the two features. Okay. So which two features we will select? Petal length and petal width. As I showed you in the pair plot, the distribution is good. They are not overlapping too much. So it's easy for the model and for us to classify the type of flower. Okay. So now here we will import the dataset iris. This is a SVM from the SVM package as SVC. As I told you, by default, SVC is going to use one versus one, OVO, right? One class versus other class, and then it will draw the plane, right? Your line, the boundary, decision boundary, and separate them. So here I am doing nothing. This is just the label encoder. We are converting our target feature, the flower name, into the label encoder 012 classes. So we can fit into the model. Okay. Here we will apply the linear SVM on the two features only, petal length, petal width. We will separate the X and Y split using the train and test split. Test size is 30%. If you want, you can make a changes in this. You can make it 20 just for your knowledge and your practice. Okay. And then we will train the model. SVC kernel is equals to linear. Now what is this? This is the kernel trick. Kernel trick is of a three type: linear, RBF, polynomial. By default, it's a linear actually. There are other three type: your RBF, your polynomial, and sigmoid. Okay, we are going to use today RBF. RBF is the purpose to convert your data from 2D dimension to 3D dimension. So it can classify clearly and we can visualize it very clearly. That's why we use it. Okay. But the first kernel by default is linear. Linear separable is easy, as I told you, right? Although today we have the case of actually three classes. So it's tough to make the linear separation too. But I will show you here. We are just writing the code for the decision boundary. The decision boundary which I showed you, that one, the dot 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 line, and then again the boundary around the your line. Okay. If you actually have seen my previous video, then you will understand. If you don't know, you did not watch that video, then I will explain you here. Let's say this is the class. Okay. So there is another class. Okay. And when SVM work linearly, it will separate like this. This is the line, but it draw the, we will draw, this is the boundary. Okay. This is the boundary. This is we are preparing here actually. Okay. So this is this distance from the line to this data point, the point which come on this is the support vector. Okay. So it try to make this wider actually. This is a goal of SVM. So it can classify the classes very clearly. So there is a less chance of misclassified. Okay. And this is called margin total. Okay. And in combined, we call it plane in 2D. But if you are drawing the same, this one in your 3D dimension, that will become hyperplane. Okay. If you, this is just the overview, so you can understand this code. Okay. But if you want to learn it at a deeper level, you can watch my first video. Okay. So we will clear this all drawing. And then we are just to model linear. We are fitting onto the grid, reshape, and access shape. So this is nothing. This is for your grid. Okay. So it will measure the shape, and we ravel function, what it does, it will flatten your array. So we can plot it on the axis according to the grades. Okay. And then we are plotting here your graph. Now look at this. This is your setosa flower. This is your versicolor, and this is virginica. So you can see this line. This is very straight. This is linear separable. Very straight, right? So this is just the line it has drawn. Okay. In your SVM. Okay. And then this is, you can consider here, this is the separation from this class. right? Separation from this class to this class, and this class to this class, and from this class to this class, and then this class to this one. Something like that, one versus one. Remember, I showed you at the start. So this is the methodology it is using, but it is linearly separable. Now, after trying the your linear separable with the your line, right? SVM, you are simple with the kernel method linear, right? Which is the default method. Now I will show you how the RBF SVM on same two feature work based on the non-linear separation. Okay. So linear separation is nothing. This is just a straight line. Okay. But here I will show you, you need to do this. Kernel is equals to RBF, gamma is equals to scale. Gamma is what? Gamma is the your line, which is very important. It helps to like create the boundary maximum to classify the two classes. Okay, like here I will show you. Here we go. So your gamma controls the width of the Gaussian bell-shaped curve used to map the data in high dimension. Okay, like look at this one. Here you can see this is a straight line. When once it is a straight line, if your two data points are going here, it is not going to linear, non-linearly, right? Non-linearly something we can say the line can go like this way, something like this. Okay, so it is trying to cover up the making the more like the high dimension, right? The bell curve shape, so it can cover up the same class data points and put it into the same class. Okay, this is called non-linear, but in the linear this is just the straight line. Okay, so this is the difference. So now if we go down, you can use it. This is a default scale, but you can make the changes in the gamma value 1, 2, 3. You can try. I will show you the interactive graph too. You can try with that one too. Okay. And then we are just fitting it again and look at this. Now you can see this line is not like straight. It is something going in this way. Something like this, right? It is not like this. Right? So this is non-linear. Although you can see it will not show us the too much big difference because we need some overlapping more data points. If we have a more noise in our data set, then it will show more clear. Okay, this is just because of our data set here. But if you want to compare here, you can see the gray, the your versicolor, right? Virginica. Virginica data points 3 we have on the this side of the class, like it is overlapping the versicolor flower. But if we have here, this is also the same, but now it is start touching this one, right? This one. Here is this one. Okay. Although it's almost same, there it is showing very less difference just because it is the data points is not too much overlapping. But you can see the difference with the line actually. You can see this is the little bit wiggly like this. Okay, this is not very straight. Okay, and then we will jump on to now you have seen the first linear separable 2D, right? And then you have seen the non-linear separable using the kernel trick, RBF and gamma value scale. You can change the value as I told you. What is the gamma? This is the your bell-shaped curved Gaussian, right? So it can cover up the maximum your data points belong to that class. It makes the more space, right? But if you are like the higher value of the gamma might be harmful for the model because it will become too specific too. Okay, so in that scenario we use another method along with the gamma, that is a C. C is what? This is a regularization method. Okay, so now first we will talk about the 3D scatter. Till so far we have used the two features 2D, right? With the linear separable and non-linear separable. Now we are going to convert the 2D data into 3D. How? We are going to use three features now. We are going to use petal length, petal width and sepal length. Okay. And then we are fitting onto the model with the RBF again. So this is the output. Right? So this is separating this one very clearly. it is a little bit more like a good separation we are able to see, right? But like here, this is the third feature, sepal width. What we have taken, sorry, sepal length, right? And petal width, petal length. So this view is also good, right? So we have considered the three features. It seems to be same like we have used the two features. It is not making too much big difference. So you can draw the graph and you can use this trick too, kernel trick too, right? Convert the 2D into 3D, okay? So you can visualize it more clearly, because this is in our case, this is not like less overlapping, but sometime you have the data set like this. So let's say there is a one class, okay, and you have the another class here like this, okay, right? It's very tough, right? So it's very tough to separate them, right? So in that you can use the above trick which I have told you, non-linear one, right? And you can also show it if you want, you have a more features, more than like the two features, then you can visualize it like this 3D, right? So it will look more good. Okay, so this is about this one. If you want to take a deeper look on this at this, then you can watch my first video. Okay, so now you have learned what the three tricks. The first is your kernel linear, which is by default, right? Linear separable, straight line. That's it. Second, we have used the same features with the non-linear, right? We are trying, but it was not showing the too much big difference, right? But the line is like this. It is not like this straight, okay? And then we have converted the 2D into 3D using three features. If it is working, then this is great, right? After that, the data, to visualize the data is tough. We can't do that, right? It's not possible. Sorry. Okay, so for your knowledge and for your testing, I have created the interactive graph for you. When you download this notebook, you can play around with this notebook, make changes in the code, or you can change the value by using the drop down, okay? And you can test the different your SVM classifying classes, okay? Hyperplane, how it is changing, okay? So here you need to use the IPY widgets as a widgets. I'm using the Google Colab, so I don't need to install anything. It is directly from IP widgets import interact and scikit-learn SVM. I have imported it above too. But if you are using the Jupyter notebook, then you need to install this one, and you need to give the extension like this, okay, to visualize this graph. Okay, so I have already written the code. If you are using the local environment Jupyter notebook, you need to uncomment these two lines. Okay, and now we are here picking up the same data set using the two values and the one target. And then I am just, I think I have written this code 2 times. That is fine. Okay. So here we are creating the function plot decision boundary. Okay. So we are picking up the by default linear C value is 1. Now what is C value? Remember, in the logistic regression, you use the regularization method, right? This is for that. Why we use it? So our model should not be overfitted and it should not be misclassifying the classes too much. That's why we use it. So what is what is the purpose of gamma? Gamma controls the width of the Gaussian bell shape used to map the data into higher dimension, right? How? Like this one. So this is the shape, right? It is just, it will control the shape, right, in the higher dimension. If the data points is coming here or here, it is not going to draw the line here, right? It will try to control it where it can find the maximum data points belong to this class. It will stop the boundary there. It will draw the boundary there. Okay. This is the purpose of gamma. And what is the purpose of C? C is for regularization method. Okay. What it does, it will control the how much the model tries to fit the data quite tightly. Okay. If your value of the C is very high, let's say C is equals to 1, 2, 3 or something like that, then your model will definitely perform very well on the training data, because it is going to learn so much and it will classify the data very clearly. Okay, something like this. If I go back here and we will draw the line like this, then it will try this one. But in this case, what will happen? It will work very good, right, on the training. But in case of your future data, your test data, it is going to be fail, because it has learned so much. If any data point come here, let's say we can make it line like this. Okay, so like this. So if new data points come up, right, there are more data points which is here, green one. Okay, so what it will do, it will try to be like a more specific to this one. So what will happen in that case? Your Virginica will overlap your other, the versicolor, right? Misclassification will increase in your future data and your performance of the model will go down. Okay, so this is the reason we need to balance the gamma value. We need to balance the C value too. Both are most important. Okay, and then here we will create the one interactive graph here. This is the same code I have used. Here I am using the just to set the your grid value for the h, the height, the step size. Okay, at what like the size it should plot the x-axis values or y-axis. This is for that one. And rest of the code is same. Here is a contour method we are using to color change. We are changing the color, right, to what is. And then here we have the interact. This is the method, inbuilt method, where we will call the over above function plot decision boundary, kernel type linear, RBF and poly. RBF and poly both are non-linear separable. This is linear separable. Okay. And then we are setting the C value starting from minimum, then maximum, then again this one. Okay. So you can change it. Gamma value is a scale, auto, standard value, auto automatically pick it up, and the 0.1, 110. You can change the values. There is a no harm. You can test it as you want. Don't afraid if you make this change, what will happen? You will see what will happen. If you found any issues, you just drop a comment. Okay. I want you to learn to just make a value changes and just test it as much as you can. It will help you to understand about the SVM very clearly. Okay. Now first, we will look at the linear one. Okay. So let me, I think we need to rerun. Let me rerun this one. All right. So this is a linear over C value is 1. So we will make it this one. Okay. And over gamma value is a scale, although it is not going to affect too much here. So you can see here what happened. This is a separated this class, right? From these two, right? If the linear separation with the in the two features, right? And when we converted it into the R, okay. So first we will play around with the C. Okay. So we will now increase the C. Okay. So now it looks better, right? So if you are increasing the little bit C value here, it is showing you the here the boundary or separation very clearly. Okay. This is what is the purpose of your C regularization method, right? To separate it clearly. And then we can just make a more changes. Look at this now. As I told you, when you increase the value of this one, what will happen? So it is going to be more specific, right? For the separation of the values of your flower type, this class, white class. Okay. It can be any flower, versicolor, setosa, or whatever. Okay. And then we will now try with the RBF. Okay. So although C value is not going to affect too much in case of non-linear. Okay. So you can change it or not. This is your choice. Okay. With the scale, this is showing this is separation, then we will make the change in the auto. Now look at this. This is more clear than your linear, right? And if we make a change with the 0, 1, it is like this. And if you make a 1, it is like this. Okay. It seems to be more clear, right? So gamma value. So it is a bell curve shape which is trying to decide and mapping the data points in higher dimension, because your 3 to 1 data points is here, right? But it is trying to cover up all, but there is some overlapping that is acceptable a little bit, right? And here if we make it 10, look at this now, what happened? So now you can understand, right? So if the gamma value is also very high, it is not going to be good for our model. Now look at this. In this case, it is able to reduce the classification error, right? This is no, there is no doubt, because it is clearly separated from the others too. But is it? It is not. It is going to be overfitted too. Tomorrow, if you have in future the new test data which contains some values, it is your this area is very small, right? You might have a wider data points here too, right? Let's say here. So it is not going to cover up those, right? So it's a misclassification. It will belong to then this class. Same with the C value, right? So if you want, you can try to change here, although it is not going to affect too much. See what is happening? No, not too much, because in case of non-linear, it is not going to be affect too much. Okay. So you need to take care about the C value and gamma value. Okay. So 1, it's okay, right? If we keep it 0 point, this seems to be okay because dimensional area is very high. If the white data points is lying here, it is trying to cover up, right? Less classification error, or it will be mapping those, right? There is a your classific, if there are outliers, it is going to be help, right? This is the biggest advantage of the SVM. I have mentioned it in my first video. Okay, that's why SVM is very very better than your logistic regression in many cases. Okay, but yes, this is not going to work if your data classes are too much overlapping and it's too big. Okay, in that case it is going to be slow. Okay, and it's very tough for the classifying it because we are not able to see the separation clearly, right? And then you can try with the poly too. Here it look like this. Poly is also non-linear, right? Although it is not, you can try this one, see what is happening. Okay, and if we here keep the 0, you can see it is a overlapping here too much, right? So you can make the C value here like this. It seems to be okay. And you can change the gamma value like this. See, it is affecting lot, right? So you need to, in case of poly, this is also non-linear. Why I have made this graph? So you can do the experiment this with this one. What you can do is just to look at the graph first, make the changes in the value, and then fit the model again, and then check the accuracy. So you will get a chance to learn too much, right? With the different values, because it is showing you clearly about the model functionality. Okay. So you just keep playing around with it. Okay. My goal was to just show you, to make you understand how it works. And this is your homework. So you can modify the kernel. You can just try the linear polynomial. We have already tried. You can try the sigmoid. Although sigmoid is just like a neural network. It's a little bit slow too, but if you want, you can try. Now you can try the different polynomial or linear value as I have showed you in the interactive graph. Fit the model again with those values, okay? And then check the accuracy. Grid search you can use to check the best value selection for C and gamma. I have used it in one of my like the video. You can check out the my machine learning playlist. Okay, grid search CV. Plot decision boundary. If you can plot the decision with the two features of the data set. Okay, I showed you the plot decision boundary, right? Over there, you can try to plot that, which I showed you on the whiteboard. Okay, use the standard scalar. We did not use the standard scalar yet, but you will use it, and just check if model performance improved. Okay, and then you can try the OVR too. Okay, here this is the code for the OVR. As I told you, by default SVC is used OVO. Okay, OVO. But if you want to try one class versus the rest of the class, if you want to your SVC to use this strategy, you can also use this one too. Just try. Okay, so you can check the accuracy here. Okay, although we did not check the accuracy here, we did not evaluate the model because my goal was to just to show you the different kernel tricks plus to show you the functionality of it. You can use a simple accuracy method for this one. Okay, if you want, you can use the classification matrices other two. If you want me to do that, I will definitely do that for you. Okay, so just look around it, play around with this one, and then I will see you in the next video. If you are new to my channel, don't forget to subscribe my channel. Keep watching, keep learning with Science Data Science, and don't forget to do the homework and drop a comment if you are all you will do, and share your notebook with me. Okay, thank you so much.